Alright, in this video we're going to be talking about the exceptions to the octet rule and resonance. Alright, so first and everything we're going to talk about the exceptions to the octet rule. So we do have a few exceptions to the octet. So there are going to be atoms that are stable with less than 8 valence electrons. So one of them is going to be boron. So boron only needs 6. Aluminum, very similar, will also need 6. And then RBE will only need 4. Okay, so atoms that can accept more than 8 valence electrons, though, will be our sulfur and phosphorus. They're able to fit more than 8 if needed. Alright, so the first one that we're going to take a look at is going to be our Bi3. Alright, so with our Bi3, the first thing that we're going to go ahead and do is that we're going to add up our valence electrons. So we are going to have our boron first. Our boron will provide us with 3 valence electrons. Our iodine will provide us with 7, but we have 3 of them. So we're going to go ahead and add all of these together. And so what we're going to end up with when these are added together will be 24 valence electrons. Now with those 24 valence electrons, we are then able to go ahead, we're able to build our structure. So we're going to start with our B in the middle, and then our 3 iodines around it. We'll go ahead and draw those lines in between, remembering that each line is going to represent 2 valence electrons. So we've ended up using 6 of our valence electrons overall. So our number that we're going to have left is going to be 18. So we have 18 valence electrons remaining. Those 18 we're going to go ahead and put around the iodines. So we have our 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So we have used up all 18 of our remaining valence electrons, and this is going to be our final structure. So you'll notice that the boron is able to hold just 6 if it's needed. Let's go ahead and take a look at the next one. So our next one that we're going to have is our BCl3. So counting everything up, we have our boron that provides us with 3 valence electrons. Our chlorine will provide us 7 each, but we have 3 of them. So adding these up again, we're going to end up with 24 valence electrons that we're able to work with. We'll go ahead, draw out our structure, kind of generically, boron in the middle. We'll have our chlorines around it. We're going to go ahead, draw in those bonds, each bond taking up 2 valence electrons. So we'll subtract 6 from here to have 18. 18 valence electrons remaining. We'll go ahead and place those around our chlorine. That's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. Alright, so we end up with no more valence electrons, and our boron is stable with just 6, so this will be our final structure. Taking a look at our last one in this will be our PF5. So we are going to have our phosphorus. Our phosphorus will provide us with 5 valence electrons. Our fluorine will provide us with 7, but we have 5 of them. So that will give us 35. That will give us 5. Add together. So we have a total of 40 valence electrons to work with. Alright, so we'll put our phosphorus in the middle because it's the only one. And then we'll have our 5 fluorines around it. Once we kind of have our general structure, we'll go ahead and add in those bonds, showing the covalent sharing. And you'll notice that we lose those 10 valence electrons in the bonds. So we have 30 remaining. With those remaining 30, we'll go ahead and place them around our fluorines. And by doing that, we go ahead and we have no more valence electrons that we're able to use. Our phosphorus will end up with 10 valence electrons around it, which is okay. All right, so the next thing that we're going to talk about is going to be resonance. And so what resonance is that it's going to be structures that can be represented by more than one electron dot diagram. So whenever resonance exists, these electrons are more delocalized, which helps to stabilize and strengthen the bond. So these molecules are going to be very, very strong and going to be very attracted to each other. All right, let's go ahead and take a look at our first one of SO3. We will go ahead, same idea before, we are going to count up all of our valence electrons. So in this first one, we'll end up with 24 valence electrons that we're able to work with. All right, now on these and everything, we are going to have multiple structures, so it is going to be a good idea to make sure that we use our space wisely. All right, so in this first one, we are going to have our sulfur in the middle, our oxygens around it. Go ahead, we're able to add in those bonds. We've used 6, so we have 18 valence electrons remaining. We'll go ahead and put those around it. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. Okay, so our sulfur only has 6 valence electrons around it, so 2 in each of those bonds, but sulfur is not one of the exceptions, and so what it needs to have is at least 8. Now, what we're going to do is that we are going to create a double bond, but what oxygen do we choose? Are we going to choose this oxygen, or are we going to choose this oxygen? Well, it doesn't really matter. So what we're going to do is that we're going to take a pair from this bottom oxygen, and we're going to go ahead and create that double. And so what we're going to end up with should just be this right here. Now, what we're going to do for resonance is that we're going to go ahead and put this into a bracket, and we're able to draw another structure. So we'll go ahead and just copy this over. Now, in this additional structure, what we're going to do and how we're going to show resonance is that we're going to take a pair of the electrons from this right side oxygen to create that double bond. And then we'll go ahead and put this into brackets as well. So that is going to show our resonance, is that whenever we get to choose where we pull those electrons from to create another bond is going to be resonance. And we're going to show that by putting our structures into brackets and using that double-sided arrow. All right, let's go ahead and take a look at one more. So our last one that we'll take a look at is going to be our O3. We'll go ahead, add up our valence electrons. So our oxygen provides us with 6. We have 3 of them. Right? We have 18 valence electrons to work with. We have our 3 oxygen atoms. We'll show that they are bonded with our 2 lines. Then I'll subtract 4 from it. So we have 14 valence electrons remaining. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Okay, so taking a look at this, our oxygens on the outside have all 8, but the oxygen in the middle only has 6. Oxygen not being one of our exceptions does need to have all 8, and so we need to create a double bond. But what oxygen do we take it from? Do we take it from the left side oxygen, or do we take it from the right side oxygen? In this case, it doesn't matter, because we are going to draw both structures. So I'm going to go ahead and start off with taking a pair of electrons from the left side atom in order to create that double bond. Whenever we do that, we'll now notice that all of our oxygens fulfill the octet rule. We will go ahead, put this into brackets, and then we need to draw our other structure. And we'll just essentially copy it over. Right, now in our additional structure, we are going to take it from the other oxygen. So looking at the right side oxygen, we are going to go ahead, we're going to have these electrons share with each other, and then we're going to put them into brackets. And that is going to be how we